Okay, so welcome back to class. The three of you that come. Yeah, okay. So, last time we talked about chapter 1 of the book, which is basically just hardware stuff. That's going to be more important in chapter 3, but right now we're going to be going over chapter 2, in which they basically just talk about some general rules of thumb when you're wanting to write fast code. Some simple mistakes to avoid, things like that. And the chapter actually starts out by talking about something called profiling. Now, profiling is something I actually have quite a bit of experience with. And basically what you're doing is you're trying to figure out where does your program spend the most time. Most of us have dealt with strand code. Did you know it spends a third of its time in right-hand side business? That's where it spends most of its time. So these spots, they're usually, in our case, they're usually loops, deeply nested loops where it just sits there and crunches numbers in that one spot for forever. And so it's typically called a hotspot. So there's quite a few ways to actually do this profiling. There are programs that help with it, and I forgot to start Linux up, so why? Okay, so while that was loading, or not. Okay, so the first way we can do this is called function or line-based profiling. Okay, the book goes into quite a bit of depth on how to use gprof. It's called gprof because it's part of the GNU, the GNU collection of stuff. So it's fairly simple to use. When you compile a program, all you have to do is add this little -pg flag. Okay, and then run your program just like normal. And at the time, it spits out a gmon.out file. And that file is actually really hard to read. It's not meant for you to read it. It's meant for the program called gprof to read it. So basically, you just run gprof on the gmon.out file. Okay, so that's pretty simple. And it spits out a bunch of information, which we will go over. The next tool that the book talks about is called oprofile. It's actually a program that runs your program for you. What it does is it basically stops the program every so often and sees, where are you? And so it keeps kind of this count of how many times it stops it in different sections. The book goes into how to use that. Personally, I prefer the tool called Valgrind. Valgrind has a tool called callgrind in it. And then when it's finished, it spits out a file. It slows your program down a ton, but it spits out a file that you can then open with kcachegrind. Unfortunately, this only works on Linux, and you have to have like all of the KDE stuff to use it, but it's really helpful, and I'll give a demonstration of that. And then there is actually what's becoming my new personal favorite, which is the random stopping in a debugger method of profiling. And we'll get into that a little bit. So let's open up our Linux window. So, last night I actually did the benchmarking project just to make sure it works. And so this is what we're going to use for our test here. And so run the benchmarking project. This is actually the gigaflops of the vector triad. Well, the first number is the size of the arrays, and the second number is the gigaflops. So, the first method to recompile this with a -pg flag. Okay, so make that, and then all we have to do is run it. And it runs, and we sit here and wait for a bit. And we wait for a bit more. Okay. Now if we look, we should have a gmon.out. Okay. Yeah. So we type, is that right? Okay, so this is good news. So we give it. Oh yeah, sorry. Okay, so what it's going to give us is what it calls the flat profile. Now, in my actual code, there's a simple Fortran code here. Here's my main program, okay? And the actual computation is done here in this function I call kernel, because it's the kernel of the code, okay? Now, gprof is basically going to tell us that it took 9.82 seconds to run main, the function main, which is defined by the G-Fortran compiler for your program. And not only that, it tells us there was no calls. So the question is, where did my function go? It's spending most of its time in that function, right? Any ideas? Well, in this case, the compiler has done an optimization called inlining, where it's taken my function and literally copied and pasted it directly into main, so there's no more function. And so that's an optimization, but you can see it screws up gprof. Gprof no longer tells us the hotspot is that function. The hotspot is the main function. And of course, it also spits out some more information. So obviously, with a more complicated program, it wouldn't be inlining everything. But that's just a basic example of how you would use it. So here it's going to tell you the total number of seconds spent in a given function. It's going to tell you how many of those seconds were spent in the function itself versus how many of those seconds were spent in functions that were called from that function. Does that make sense? Okay. And it gives you a lot more information, but that's the basic result with that. So let's change our makefile again. Back here, make it, and then I believe we just O profile. We don't have an O profile. That's cool. Where does it talk about O profile in here? Another important thing to realize is that you can get it without line information. Like it'll tell you, you spent this much time at this line in your source code, but that can get really screwed up when optimization is done, because the compiler will go and mix everything up. And so certain lines, it may be wrong. in that case. So where go? Yeah. I've never actually used OProfile, so I wouldn't worry about it. We're not going to be profiling our code too much, but it is useful to know. So there's that, and then we can run with Valgrind. Whoops. And then we tell it, okay, Valgrind slows your program down a lot. Because what it does, Valgrind actually becomes the CPU for your program. So it's a software CPU. It causes this to happen, where it goes really slow. But because it's acting as a CPU, it can now keep track of every little bitty detail that's going on in your program. Okay, so let's let it go 1,000. And then we'll just stop it there. And you'll see we now have a callgrind.out.number, and that was actually the process ID number. And so we can open that with, I hope this works, the K cache grind. Okay. And this gives us a ton of information. So, over on the left, we've got a list of every single function in our program. It's probably a little tiny on the screen, but so you can see the compiler actually does quite a bit for you that you don't know about, which is good for us. And the most important part, I like this call map. So this map, it looks better with a more complicated thing, but it actually gives you kind of boxes. The bigger a box is, the longer time spent in that function. So it says everyone that called this function, everyone that was called by this function, and then what I found to be probably the most important tool here is the source code annotation. And so we can change, I usually use the cycle estimation, estimates how many CPU cycles are spent on a given line. And we can make this relative. So unfortunately, it's not going to give us too much because everything's been inlined. But it says 100% of our time was spent in the function main. There's just lots of cool information. We got call graphs, we got callees. This is pretty cool, the call graph. So that's actually the function that starts your program, and there's another function that starts your program, another one that starts your program, and then finally we get to your program here. And so you see there's a lot going on in here that we don't know about. So anyway, I really like to use that method because it's very graphical, visual, things. It's pretty powerful. But there's another method that I tend to like better. So there is on Linux GD debugger. It stands for GNU debugger. Okay, and we can run our program using the debugger. And if you type R for run and hit enter, it's actually going to run your program. Anytime you want to stop it, you hit Control C. Okay, and the debugger stops your program. And it tells you what line you are currently at. And right now we're at line 46. Okay, and it says there's our vector triad. And then if we type C, that stands for continue, hit enter, and we stop it again. Hey look, we're at line 46. And continue. And Control C. dang, that line 46 sure does seem to take up a lot of our time. Okay? So I actually really like this method because it gives you it basically does the same thing, but it gives you very visual feedback. You are at this line right now when you stop this. And so you just stop the program randomly, like 20 times, and you get an idea of the distribution of how much time is spent in each part of your code. And so you know exactly where to focus. So that I found it to be extremely handy for profiling code. Alrighty, moving on. Now we're actually going to talk about optimization. And we have this. Whenever you're talking about optimization, someone will always bring this quote up, which is, premature optimization is the root of all evil. Okay, this was said by Donald Knuth. He wrote basically the original book on programming. He invented LaTeX. He's just a genius. Anyway, but what he's trying to say here is people spend so much time nitpicking, trying to, if we do it this way, it'll go faster. They spend so much time on those small, stupid things that they don't get any work done. They make their code hard to understand. It can't be fixed later. And so that's my warning. When you're talking about optimization, you need to be careful. Make sure you're not going too far. Because there are other things to consider other optimization. And sometimes trying to optimize things makes it worse in the end. So I just wanted to talk about the general overview. How do we write software in general? Okay? If we wanted to write a piece of software, the very first thing we'd have to do is determine our specific requirements. What is this software doing? Why is it doing that? What does it need to accomplish? Does it need to accomplish it in a certain time? Does it need to be user-friendly? Does it need to... all that kind of stuff. Then you have to research libraries, research algorithms. And what I mean by that is look and see what the computer science people have done. They've run into most of the same problems that you're going to run into, and they've come up with some really good solutions. And of course, when you're looking into using a particular library, you have to think about, is it going to be worth learning? Is it going to take more time to implement? Is it going to be buggy? Is it going to take too long to run? Is it going to... and then is it going to be flexible? Can we use it, change it later in the future? Then you create your software, making sure it works along the way. And that's the most important part. Software that works is better than software that goes fast and is wrong because you tried too hard to make it go fast. After it works, you've got it all done, then you can profile it to find the hotspots. And you can use optimizing techniques, but actually most of it, you just need to change your approach. And that's the optimizations we're going to be talking about today. And so kind of my point in the end is don't sweat the small stuff, okay? Get your big rocks, get your big ducks in a row first. Then you can have the little ducks. So, talking about optimizations, and these are all in chapter 2. I'm going to turn this on now that we got the little pictures out of the way. The very first optimization they talk about is do less work. Now that just seems kind of obvious. Just do less work. And they give an example, is a loop that checks a number of objects to have a certain property, but all that matters in the end is that any object has the property at all. Okay? And so basically they say, there's like this loop that's looping through something and checking stuff, and there's a flag, and when you find something, you set the flag, but then you keep looping through everything else. Okay, and then after the loop is done, you check the flag. See, that's kind of ridiculous because we already know. And so what they do, they put an exit statement in the middle of the loop. Instead of using a flag, you can just exit from the loop. Ta-da, we found it. So, that one just seems kind of obvious, but there it is. Now, this one is actually really, really useful. Avoid expensive operations. So there are certain operations, certain functions that are actually quite expensive in terms of computing power. Okay, let's see if I can't get this thing to come over here. There we go, that's cool. So we have your functions, sine, cosine, tangent. Those typically take hundreds of compute cycles to actually work. And then another big one, which is kind of surprising, is the POW function. And I actually have an example of this. I've sped up Dr. Katz's code a lot by finding this. He had the following statement in his C++ code. The POW, some big nasty thing to the 1.5. Okay? So that seems pretty innocent enough, right? Any ideas on how we make this go faster?
Just do to the 3 halves? Or it's cubed and then square rooted?
Exactly. So I changed this to x equals the big nasty thing, okay? And then x equals x times x times x, and then x equals the square root of x. Okay? Because whenever you're doing a power to a decimal point, it has to use a really slow algorithm to actually do it correctly. When you're using an integer, there are shortcuts it could take. I found another one later that was just power to the 3rd power, and that was still going slow. And so I actually changed it to this, and I got 6 seconds out of it.
So, is this in Fortran?
This is in C++,
Okay.
but the same rules apply for Fortran.
Well, so if you're in Fortran, you can do like the double asterisk, and that's
essentially the same thing.
okay.
Yeah, so if you're using the double asterisk, make sure you're using integers as far as you can, as much as you can. And in fact, if you look at what G-Fortran uses for PAL, it uses the exact same thing that the C++ uses.
Oh, okay.
Behind the scenes, so you don't know that. So that's something to really look out for. Now, what I mean by pre-compute expensive functions, let's say you have a range of, say you have to compute some trig functions over an array, and you have to do that several times. Okay, so what you do is make a separate array, compute that, and then all you have to do is pull those numbers. What? Yeah, exactly. Make a table. As long as you have, you don't have to trig function anything. If you have a set number of values that you can trig function, then you can make a table. A lookup table is what they call it in the CS world. So, the next optimization, shrink the working set. And this basically means one of two things. Either change your algorithm or use smaller types. And this only using smaller types could or could not make a difference.
By the way, just so you know, there's an option on there to erase all ink on the slide.
Oh, did you look at that? Okay, cool, thanks. Alrighty, so what I mean by change your algorithm, and this is something I want to talk about. Let's say you have a bunch of objects and you need to sort them. A bunch of integers that you need to sort. How are you going to sort them?
What do you mean you need to
Standard
sort?
Thank you, Mr. C++.
What do you mean sort then?
So we have a 2, 3, 1, 0, 10, and we want these all to be in order from 1 to 10. Okay? So 1 here to 10 here. How are we going to sort them? How would you do it?
Well, you're probably expecting us to say, just loop through it every single time and find the minimum, then the next one, then the next one, then the next one.
Yeah, that is a valid method, but that is what they call an O(n) squared method, I believe. Am I right in that? And so what that means is, this is a notation that computer science people use. It's called big O notation. O(n) squared. Okay? So your suggestion to find the minimum, move it to the end, find the next minimum, move it to the end, it may not be O(n) squared, but it's probably pretty close. What that means is there are n elements. Okay? In this case, 10. We have 10 of these elements, and we have to loop through them n squared times in order to sort them in the end. Now, sorting is a topic all on its own. They have dozens of different sorting algorithms, and each has its strengths and weaknesses. I think standard sort uses a heap sort.
Quick.
It's quick.
It's like a combination of a bunch of like.
Oh, they use a combo.
Big, it'll use one and get it down small, and then use one of the.
Okay.
It does all kinds of crazy stuff. But I think it's mostly quick.
Okay. Yeah. So, when you're dealing with Fortran or C++, you typically don't have a standard sort. Not C++, C. You don't have a standard sort. Most modern languages, Python and Perl, they have just a sort function, and you don't care what it does as long as it works. But that's what I mean by change your algorithm. Algorithms always come with some cost, and you want to get this down as much as possible. The best would be O(1). It means it's constant. It doesn't matter how long it is. It operates in exactly the same amount of time. Usually, algorithms will have something like this. Okay, that's generally the best that you can hope for is log n. So it takes n, it takes the log of it, and that's how long it's going to take. And it grows. N squared is a bad thing. You don't ever do an n squared algorithm if you can help it. Now, smaller types, what that means, that really only helps if your compiler is able to use the SSE instructions. Ta-da! Okay, so I want to talk about SSE for just a second. SSE is a funny little thing. They have a register in your CPU that is 128 bits. Whoa, where did that come from? Okay, big line. How did I do that?
I don't know, but remember it.
Okay, let's back up. Slideshow. Okay, so let me draw my square here again. Come back here. This is typically 128 bits. Okay, so for this one, and then they have another one. Now, a double in C or C++ is typically 64 bits. A float is 32. Okay, I don't even know if there's a short float, but if there is, then great. But the way an SSE register works is it's actually going to, let's say you had a loop, like our vector loop, A equals B plus C times D, okay? We have these big arrays. What it's actually going to do, it's going to stuff two numbers into these two registers. So we have one number, two number in here. And it's going to add both of them at exactly the same time. And so theoretically, if everything works properly, you get a 2 times speed up just using these registers. However, what if we're using floats instead? Then we can put 4 of these things in here and we get a 4 times speed up because it does 4 additions at exactly the same time. This is a relatively new introduction to the computing world. People call this vectorization. But by using smaller types, hopefully you can stuff more things into these SSE registers. Also, it saves on memory because you can fit more of them into cache as well. So a short int is typically 2 bytes, which is 16 bits. And so you can literally fit twice as many numbers into the cache at that point. So then, simple measures. Elimination of common subexpressions. If you have a big, big, long equation, and you have something like x times d plus x times d squared, what's the common subexpression in here? It's x times d. Okay, so if the compiler's stupid, it's going to compute x times d, and then it's going to compute x times d again. And so we can be nice to the compiler and say, oh, let's just do...
Store it in a different variable.
Right, put it in a different variable and do that. Okay, this comes in most handy when we're using expensive things, sines or cosines or square roots, things like that. Okay. Some people, it's easy to believe that this is the compiler's job, and it is actually part of their optimizations. They do look at things like this, but oftentimes if your math is too complicated, the compiler's just going to give up and go home. So, and third, avoid branches. Branches are always problems. They slow your code down. And the basic rule of thumb is don't put if statements in loops if you can help it. Which is funny because it actually goes against our do less work, where we said put an if statement in the loop to get out of the loop. So, it kind of depends on the situation. But the reason being is that every time it comes to a branch, it has to stop. The computer has to stop and say, okay, which way am I? And then it has to look up the correct direction. And then it has to go get the instructions for that direction, pull them into the CPU, and run them. So every time you come to a branch, there's a slowdown because the CPU has to stop and figure out what to do next. Okay, so this is what I just talked about. The single instruction multi-data instructions. Basically, it means you have a single instruction, which is add 2 numbers. You have multiple data. You have 4 numbers. And so you'll do it to all of them at once. I will note this only helps for code that is not memory bound. Okay? Memory bound code, you're stuck by the memory, so it doesn't matter how fast you can compute things. Use small types if possible, as I just explained. Now, in order for the compiler to be able to use these SSE instructions, you have to write nice loops. Tight loop kernels with no loop carried dependencies like we talked about last time.
So, question about that.
Yes.
No loop carried dependencies, that's not always possible, right?
It's not always possible, but there are ways around it. However, with that being said, sometimes if you write code that cannot be vectorized because of loop dependencies, but has a higher cache locality, can be faster than the vectorized version. Where you have to mutate your loops in order to fit them into an SSE register. And it's at this point I want to talk about array of structures and a structure of arrays. So let's say we needed a list of points, x, y, z coordinates. How are we going to code that up? Make a struct, okay? Let's make a struct. Struct point, and we'll have, we always use doubles. Any idea why we always use doubles?
You get a better precision in your end calculations
Okay, why?
because they carry more.
They can carry more data. I think.
They carry more digits, first off. And secondly, it helps deal with round-off error.
Yeah.
Okay, because you never can trust like the last 5 digits of a double precision number because there's so much round-off error going on. So, and a good algorithm, good numerical method actually reduces round-off error as it runs. So there's that too, but you're always going to get a bunch of randomness going on. So we have double x, y, and z. Right? Have I done that right? Okay. So, then a bunch of these. So how are we
Make an array.
make an array? So we have point my points, and we want say 100 of these. Okay. So now how are we going to go about and do computation? Let's say we wanted to find the vector magnitude of the displacement of these points. We'd probably make a function, but the idea here is we would do something like this. The square root, we'll just call it p for now. And oops, z squared, right? Okay, so this method is called an array of structures. So that's this one here. And it actually, using this method makes it very hard to use vectorization. Because things are not lined up nicely. So it's a little hard to explain, but I'll try. So in memory,
Just when you say things aren't aligned nicely, in my head they are.
yeah, because it's easy to think about points this way,
So
right?
explain why they're not.
The problem is with the memory, okay? So
Oh,
so if we have 4
so it's
points,
in line. So it's x1, y1, z1, and then x2, y2, z2. Whereas if you did
it's lined up like this.
if you did a structure of arrays, it would be x, 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 y, 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 z, 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 z.
Right, exactly. So in this view, the reason is SSE instructions, they want to take a whole chunk and load it, and take a chunk and load it into a register. Okay? And they can't do that here. If they wanted to do, so if this is the SSE register here, and it's going to want to take 2 x's plus 2 y's, okay, plus the 2 z's. This is what it wants to do. Okay, but in order to do that, it's got to go here, and then it's got to skip and go here, and it's got to do that for all 3 of those. Okay, which makes it very hard to vectorize. It can still be done, but it's not as efficient. So what the Intel optimization guide, and I think I've put that on Canvas, suggests is instead of doing that, what you should do is have an entire array of just x's, an entire array of just y's, and an entire z.
So, the advantage to doing an array of structures is that it's really easy to make it dynamic, so you don't have to define how big it is right when you're defining the structure. So can you do that? Does that make
I'm not
sense?
sure I understand.
So when you make a struct of XYZ, no, it's just XYZ. You can make it as big as you want dynamically. Does that make sense?
So
You
you're
can define it as a dynamic struct, dynamic
array.
array of the struct.
Okay. Yes.
That's really easy to do like that.
Right.
It's not as easy this way. Is that correct?
Here you have to do it 3 times. It's about the same thing, but you have to allocate 3 different chunks of memory rather than 1 chunk of memory. Does that make sense?
Right. I mean, they're all going to be the same, but
Right. We hope they're all the same. Otherwise, we have a bug in our program.
okay. Sorry, I was just thinking out loud.
Okay, that's fine. So yeah, that's if you want to make sure that it's easy to use these SSE registers, which supposedly go faster. You want to do the structure of arrays formulation here. And in fact, you can combine the 2 approaches. Okay, and here's how you do it. You have, so that way you can use one or the other depending on, the situation that you're in. The first thing you do is you allocate your memory in this fashion. Okay? And then you create a struct called point. And in C, you do it this way. You make a pointer to x, y, and z. And then you allocate a bunch of points and you point them to these lines. Does that make sense? And so that way, if you want to deal with a single point individually, you can. And you don't have to worry about, oh, this point is indexed at I, because the pointers take care of it for you. Does that make sense? In C++, I would use references instead of pointers, but it's about the same thing.
So you just have 2 pointers to the same, like, you have like an array pointing to all the x's, but then you also have like each set of points.
Right, and so that way, when you're dealing with them in a row, you just use the arrays, and when you're dealing them 1 point at a time, maybe for an unstructured grid method, you can use that. And so that way you still retain the ease of use from the point, but you still retain the speed from the structure of arrays. So, does that make sense? You're giving me a quizzical look.
I guess I'm just confused. How do you? I don't even know how to phrase this question. How do you, you have to define how big it is at some point, right?
How big the array of points is?
How big the struct is. Yes.
Okay. So you just do that with an allocate statement, new statement. If you're in C, you use a malloc statement, but
Okay. I think that makes sense, actually.
and in C++, I'd actually be using a vector, probably, the vector class.
Vector class, okay.
So, now we need to talk about the role of compilers, or in other words, your relationship with the compiler. Usually it's a very rocky relationship because the compiler is very stubborn. But every compiler has certain optimization settings and flags, and it's usually not your job to try and tweak all those flags individually. Most compilers provide nice little -O flags for optimization, and there's different levels. Level 0, 2, and 3, at least for the GNU compilers. And they do different things. Sometimes O2 can be faster than O3 because O3 over-optimizes and actually makes things worse. But generally, I just use 3. Okay. And it's important to know that this can screw up your debug because things get moved around and it's very difficult to debug. So, rule number 1 when you're programming, assume the compiler can figure it out. Okay? It's generally a better idea for you to be able to understand your code than to try and optimize your code. Especially micro-optimizations can really make code hard to read. And so when you're thinking about it, when you're working on a code, generally better to be able to understand the code and make sure it works. Okay? And assume the compiler can make it run nice and fast. Rule number 2 is assume the compiler cannot figure it out. And what I mean by this is the more complicated you make your lines or stuff, or the more general you make your code, the worse the compiler is going to optimize it. So take, for instance, the offset. I actually didn't show these pictures last time, and I should have. But I was talking about that scaling loop. Everyone remember the scaling loop? Which you do for your project? Where'd it go? Okay, so here's the megaflops. So just for the camera, so see. So the scaling loop with the loop carried dependency, we had AI equals S times I minus 1. Okay? So there's that. And then there's just the plain and simple scaling loop. Then there's the pseudo dependency. And then there's the general version where we have I plus some offset. Okay, just want to read this so everyone remembers them, because I'm going to write them now. Okay, so for the simple scaling loop, our megaflops, as the arrays grow larger, look something like this. Okay, it looks about like the vector triad. Now, with the real dependency, the I minus 1, okay, it's going to look like this. Okay, that real dependency really slows down our pipelining. Now, I want to draw the offset, where the compiler doesn't know what the offset is. And so here they have offset equal to 0, so there actually is no offset. It actually looks like this. Okay, you'll see it doesn't go as high. Even though it's exactly the same thing in the end, the compiler doesn't know, and so it can't be nice. And then with the real dependency, so we have an offset of minus 1. We get this. Because it doesn't know it doesn't know enough. And even with the real dependency, the compiler can still optimize things for us and get us at least a small burst of speed here. But if it doesn't know that, it has to stop, basically. It has to stop optimizing altogether.
It's better to hard code stuff than to...
For speed, it's better to hard code stuff. Yes, and there are programming practices in which to hard code stuff, but still leave it generic. It's a little complicated, but it can be done. So And that's actually one of the techniques I used for optimizing the strand code. Because the number of equations in the system layer knows what the number of equations is, and yet it wasn't hard-coded in there. So it all depends on information, So I hard-coded that in there using an enumeration. So I didn't have to change the variable name. I just turned it into a number. And I don't know how much it helped, but I thought it was a good idea. Okay, so I'm going to talk about some common compiler optimizations. Are we out of time? We are. Okay, well then I will get to all the rest of this on next Tuesday, next week. So, before everyone goes, I will be posting the project. It'll be due end of next week. Okay, and I actually have done it. So,
Are you posting it tonight?
yeah, I'll post it tonight. I need to make a few tweaks to it. But I just want to show everyone kind of what they should be getting. Okay, so I should just write this down into a script, but I haven't. And megaflops. Okay. So I did this on my lab computer. And so we can clearly see the wind-up region until it reaches its max peak. Now this is actually in gigaflops here. This is a 3.4 gigahertz computer. So you'll see I'm getting up to 3.4 gigaflops in the L1 cache. And then we come out of the L1 cache into the L2 cache from here to here-ish until it drops down to the L3 cache, which is kind of in this region until we finally peter out into main memory. So that's kind of the plot you should get. Don't worry about these little blips. I don't know why they happen. I really don't.
So if you ran it again, would they be in like different places?
Yes. So if you wanted to get clean results, you should run this 100 times and average it. And I didn't do every single number. You saw how fast it ran. So I actually did in between each one of these 10 to the 4th, 10 to the 5th, 10 to the 6th, I ran 1,000 runs in between each one of these. Just to try and make it a little more evenly spaced and not have to run a billion cases. Excuse me. So anyway, that's kind of what you should be getting. And it's funny because it looks almost exactly like what we get in the book. So I want you to do that for 2 different computers. I'll post that up as soon as I can. It's going to be a PDF. I'll just on Canvas. And compare 2 different computers. Talk a little bit about why one is better than the other. Sound good? I did get an email from CHPC. Kingspeak is having problems right now. So hopefully we'll get that fixed soon. Oh, and Ash. Okay. So anyway, there's that. So thanks for coming to class, everybody.